So my name is Jacob. This is my colleague, Ryan. We're both from a company called eSentire. We do MDR. We're a Canadian MDR provider, so we do work with EDRs on a daily basis. And why are we doing this talk? So a little short story. About 10 years ago, 2015, is when we first started kind of working with EDR at eSentire. We were, at that time, EDR was new. The security monitoring space was dominated by network security monitoring. And the common wisdom at the time was that that was the better way to go, because if you have an intrusion where a host gets compromised, you can't trust anything on that host anymore because it's not controlled by the attacker, right? So you want to have a source of telemetry and visibility that's independent of that. And so that was the common wisdom. But then when we started working with the EDR and seeing how rich the telemetry was and how effective seeing all that context was for reconstructing incidents and containing them in real time, it became very obvious that EDR was going to be a game changer. And so fast forward a few years later, we were now fairly mature in our endpoint security practice, and we had learned a few important lessons. One of them was that in order to be able to contain incidents before they get to the final end stage, it's very important to focus on the intent of the activity that you're looking at. And one of the most clear indicators of malicious intent is the attempts to bypass security defenses, because there's really no benign explanation for that activity for the most part. So we found that when we were looking at things like PowerShell activity or command lines, if we saw attempts to obfuscate or to turn off antivirus or any of those sorts of defense evasion tactics, that was a telltale sign that we were looking at malicious activity. And then fast forward a few years later, and now EDR was an established form of network of security monitoring. And the attackers had learned that because it was so effective and they were being stopped on a regular basis, they had now learned that they needed to focus on the EDR specifically and target it in order to increase their chances of actually achieving their goals, right? And so because the EDR now became a direct target of the attackers, we were forced to adapt and start studying the techniques that they were using to disable the EDR and increase their chances of achieving their goals. So just a quick distinction. So when we talk about EDR bypasses, it's a vague term. So we're not talking about evasion in this talk. So we're not talking about things like process injection or inline unhooking. These are the sorts of things that attackers do in malware when they try to execute their payload on the initial host. And that is an interesting topic. We're just not going to be focusing on that. We're going to be focusing on the tactics that the attackers use once they're already on the host. They have control, and now they're trying to either disable the EDR post-exploitation or operate in such a way that the EDR is not monitoring their activities, and so they stay invisible. So we're going to be exploring those kinds of techniques here. We're going to be making assumptions about the attacker, right? So one assumption that we're going to be making is that the attacker is already on their host. They have control of the host. They have code execution. And we're actually going to also assume that the attacker has local admin privileges. So either they have credentials that are already local admin on that host, or they executed some sort of local privilege escalation, and they obtained that local admin that way. And we're also going to be assuming that they have some sort of way to control the host, either like a remote RDP session, some remote shell, or a remote admin tool like PSExec. The security boundaries that we're going to be kind of exploring here, there's a couple. So user to kernel. So we have a regular user. Maybe they have access to applications on the desktop. They can interact with the operating system, and they want, if it's an attacker, they will want to see if they can get access to the kernel, because once they get access to the kernel, they can bypass all the EDR defenses and they have complete control over the machine. That is an actual security boundary that is enforced by the operating system. And so the attacker will have to kind of overcome that if they want to do some damage against the EDR. There's also another kind of quasi-security boundary called process protection. That's a technology that was introduced in the recent versions of Windows. And essentially, the intent of that mechanism is to make certain processes that are critical to the operating system or to the security solution be kind of isolated and protected even from administrators. So, the attacker might have local admin, but if they want to do something malicious with a protected process, they would not be allowed to do that unless they have kernel access. Right, so that's another mechanism that's enforced by Windows, the operating system itself, and we'll be talking about that a little bit later on, but we won't be focusing on it too much. We'll be focusing more on the kernel, and we'll explain why. Now, the EDR solution itself has self-protection mechanism as well. They usually fall under the umbrella of tamper protection. And so those are things like the attacker could try to turn off the EDR, uninstall it, maybe change its configuration so that it doesn't work anymore, or turn off certain components of it. And so the tamper protection mechanisms or self-protection mechanism that the EDR has would be trying to prevent that. And one kind of important non-security boundary that's important to talk about is local admin to kernel. So Microsoft considers a local admin to legitimately have access to the kernel. So if you come up with some sort of tactic that actually achieves that, where you're a local admin and you find a way to do something in the kernel, well, technically Microsoft says that you're allowed to do that, and it's not really an issue, which is kind of a problem, because in the context that we're talking about today, where the local admin is actually a malicious attacker, once they get access to the kernel, they basically have unrestricted access to everything, and we don't want that. We want to protect the EDR from that malicious local admin, right? So because that's kind of a recurring problem in our scenarios, and we'll be looking at kind of the implications of that and how we can mitigate that. Okay, so kind of the standard way to bypass EDRs, you probably hear about all the time in the news, is EDR killers, right? So you might read about an article about, ransomware group XYZ has some super duper EDR destroyer that is able to stop, any kind of security, the major security solutions, AVs or EDRs. And there's usually a couple of ways that these EDR killers work. So one very common way is called bring your own vulnerable driver, BYVD. The way that works is that in order to gain access to the kernel, to execute any code in the kernel, you need to load a kernel driver, right? And there's a protection mechanism in Windows that forces all kernel drivers to be digitally signed by Microsoft. So technically, a malicious attacker can't just bring their own kernel driver because it's not signed by Microsoft, it's not going to be allowed to be loaded and run. So what the attackers do is they try to find kernel drivers that are legitimate from legitimate products that have legitimate digital signatures, but they have some sort of bug, some sort of vulnerability that's able to be exploited. And usually it's either something that allows code to be executed in the kernel or arbitrary read-write into the kernel memory. And the way they usually exploit that is in the kernel, there's a flag variable that controls whether kernel drivers need to be signed or not. And usually that's enabled by default. So what they do is they exploit the vulnerability in the kernel to turn off that flag. Once they turn it off, then they can load their own unsigned driver, and now they have full access to the kernel. So that's one way. The second way is kind of related, but it's called living off the land drivers, or LOL drivers for short. And it's kind of similar, except the driver doesn't necessarily have a vulnerability. It's a legitimate driver, again, that's signed by Microsoft, and it's from a legitimate third-party product, but it might have some functionality that the attacker might use to accomplish one of their goals, right? So, for example, let's say that the driver has the capability to kill arbitrary processes in user mode. The attackers can either reverse engineer the driver and figure out how to invoke that functionality, or they might kind of observe the commands that are sent to the driver by that legitimate application and try to kind of replay that themselves. And they can use that functionality, for example, to kill an EDR process, right? So again, that's kind of a similar issue as with the vulnerable driver, but it's not really a vulnerability, it's just abusing a legitimate driver. So that's kind of the most common way that these EDR killers work. And you can see that that's an example of this local admin to kernel security non-boundary, right? So Microsoft actually is working towards mitigating that issue somewhat. And so in the most recent versions of Windows, they have technologies in there as part of the virtualization-based security. One of those components is called HVCI, which is short for hardware, I think it's hardware virtualized code integrity, I believe. And the idea is that a certain portion of the kernel is separated off from administrator access. So now they're basically establishing a security boundary between the kernel and the administrator. And inside that separated boundary is where kind of the policy enforcement is isolated from the administrators. And one of the ways that can be used is to implement like a block list of these vulnerable drivers or low drivers that these EDR killers use. And once that block list is implemented, then if a malicious attacker tries to load one of these drivers, it will be blocked, and they won't be able to achieve their goals. And the point of having all these virtualization technologies is that it makes it difficult for the attacker to actually disable those policies, right, with just local administrator access. So in combination with the secure boot and HVCI and WDAC policy signing, you're able to implement these block rules and make it difficult for the attacker to turn them off, essentially. And actually, do any of you actually use this technology in your organizations? Anyone? No? No, the driver block rules, signed WDAC policies, HVCI, no? Okay. So it looks like that's still not very well implemented. It is a new technology, and it is difficult to manage. So the hope is that as the deployment of this increases, it's going to be more difficult for attackers to use these EDR killers. Okay, so EDR killers, that's kind of like a high-end way of doing these EDR bypasses. Actually, is there any baseball fans here? Yeah. Okay, a few. Anybody seen the movie Moneyball? Okay, that's it. A few, okay. I'll just explain very quickly what the theme is. So the theme is, I think it's around the year 2000 or so, in baseball. Baseball is essentially becoming kind of like a pay-to-win sport, right? So there are very rich teams, like the big market teams that could afford all the superstar players that were making tens of millions of dollars a year. And then there were the very poor teams that couldn't afford those players. And so one of those poor teams was the Oakland A's, who had a general manager called Billy Beane. And he came up with this idea that they couldn't compete with the big rich teams on buying those expensive players. But what they're going to try to do is use statistics and analytics to find kind of undervalued cheap players that would be able to compete with those overpriced superstar players. And so they figured out a way of evaluating players and their impact on winning baseball games in a way that no other team had done before. And they were able to identify players that were considered either like defective or kind of undervalued. They went out and got those players, and they tried to figure out if they could compete with the rich teams with those players, right? I'm not going to spoil it for you. It's a really good movie to see what happened. But that's kind of the idea that we came up with for our project here that we're talking about now. So if you can kind of look at the EDR killers as kind of like the high-end, the superstar players, we were trying to see if we could look for some kind of more cheap ways of doing this, the same thing, that doesn't involve kernel drivers and reverse engineering and exploits. And so so that was our project. That's what we're going to kind of present today. And so we kind of know what we want to look for. Now the next question is, where do we look for this, right? And so one thing that helps here is to understand how the EDRs work and how they interact with the operating system components. And actually, one way that we try to make this process a little bit easier for us is we actually came up with a tool. So Ryan wrote a tool that helps us to kind of enumerate the attack surface of the EDR product, and it will make it easier for us to identify areas where we can look for weaknesses and potential bypass attempts. So I'll hand it over to you.
Thank you, Jacob. All right. Howdy, folks. So thanks for coming to our talk. We'll be sharing a tool that, as Jacob mentioned, we'll be sharing a tool we've been developing for attack surface reconnaissance against EDR agents on Windows. The tool is called Surveyor. Surveyor comes as two components. There's a user mode component written in Rust and a kernel component written in C. And what Surveyor does is it collects telemetry across 13 different areas of the Windows system to paint a picture of the defensive monitoring capabilities of the agent on the host. Think of Surveyor as pre-engagement reconnaissance, so giving you an idea of what initial attack vectors might be more likely to succeed, which initial attack vectors might be less likely to succeed, and the overall defensive monitoring capabilities of the agent, derived through data. So as Jacob mentioned, sort of this Moneyball approach. As I mentioned, the tool collects telemetry across 13 different categories of the system. We'll be diving into a few of these categories in detail, talking about how the telemetry is collected and what the relevance to the attack surface is. So we'll start with some process telemetry. We'll move on to some driver enumeration. We'll dive into the kernel for some kernel callbacks and some ETW-based analysis. And we'll return to user mode to talk about some network telemetry, some registry enumeration, and some other fun stuff as well. All right, so starting with our process telemetry. Our process telemetry was designed to paint a picture of the attack surface of user mode processes on the system. So we start pretty simply with create tool help snapshot to get a list of all the processes running on the system. We then enrich that list of processes with some WMI queries to get things like command line arguments for the processes, sort of get a better process object going. We further enrich that object with a query into our driver component to get accurate PPL data for the process. And finally, we store a map of all the loaded modules for each process as well. So the key insight here is accurate PPL data, so having accurate protected process light information for each process. As Jacob mentioned, process protected light is a kernel-enforced Windows security mechanism that provides protection for user mode processes against certain behaviors. So specifically things like process injection and memory manipulation. So having accurate PPL data is crucial to understanding the attack surface of the user mode processes on a system. If you see a process is running as PPL, we know that that's sort of where the investigation chain ends for that process. We won't be able to interact with it further, barring some kernel manipulation, which is possible, but that's not the focus of what we're talking about. So moving on to our driver enumeration. Our driver enumeration is leveraging the NT API. So NT query system information with the system module information flag. And what the system module information flag does is it returns a list of all the loaded drivers on the system along with their load addresses and sizes. So what we're able to do with this list of loaded drivers is we can identify all the kernel components of an EDR on the system. Furthermore, we can leverage the load addresses in the next piece of analysis we'll be talking about, which is kernel callbacks. So moving on to our kernel callbacks. Windows exposes a number of APIs which allow drivers to register callback functions against key system events. So think things like process creation, thread creation, registry modifications, and stuff like that. So Windows will trigger these callback functions whenever these key system events occur. And though these callback functions can sort of perform whatever behavior that is codified into them by the respective driver which is registering them. So having an understanding of which callback functions which EDR agent is registering is crucial to understanding the attack surface on the system, as it directly informs you of the sorts of telemetry that the EDR agent is able to monitor for. So think of examples like if we see that an EDR agent isn't registering registry modification callbacks, we know that registry modifications might be a more likely attack to succeed against the EDR. So we wanted to give a shout out to another project here called Telemetry Sorcerer, which was doing similar enumeration to our project. The key differences are in how we actually find the callback tables in memory. So Telemetry Sorcerer took a pattern matching approach, looking for hard-coded patterns against particular Windows builds. We're leveraging Microsoft's symbol server to download the debug information for the kernel image on disk, and then using that debug information to look up the actual addresses of these kernel tables in memory. And then via our driver, we're able to read these kernel tables and parse them in user mode. And what we ultimately end up with is a list of function pointers, which, thanks to our driver enumeration from the previous slide, we can map to particular system modules. So ultimately, that paints a picture of which system modules are loading which callback functions, which directly tells us what sorts of telemetries these EDR agents are looking for. And that directly informs the sorts of attacks that we can make against these EDRs, which might be more successful or might be less successful. Sure.
Are you making any assumptions on the OS, the version of the OS?
The one piece of telemetry that is OS version specific is our PPL telemetry. Everything else is version agnostic for.
So it doesn't matter if it's on Windows Server or Windows Workstation?
Correct. Yeah, so the tool will run in both environments. Yes, so I think that covers our kernel callback section. The key insight is that it's a direct indicator of the telemetry available to the EDR agent. So moving on to ETW. ETW, for those that aren't familiar, is event tracing for Windows. It's a logging facility in Windows which provides session-based pub-sub semantics for these various ETW sessions. I think things like the security event log, for example, or the threat intelligence event log. These various ETW feeds are gold mines for behavioral data on the system. So what we're able to do in the kernel is that the entire ETW state for the system is stored in a kernel structure. So we can enumerate that kernel structure and we can get a map of ETW sessions to user mode processes, which tells us which ETW sessions these various user mode processes are consuming. And that directly informs the sorts of behaviors that the EDR agent is able to monitor for. So if we see that an EDR agent user mode process is looking at the security event log, for example, then we know that all the telemetry that's available in the security event log is available to the EDR agent. Similarly, if we see that the user mode processes for an EDR agent aren't looking at any event logs, we know that certain behaviors might be less likely to be detected by the actual EDR agent. So returning from our sort of kernel enumerations, we also perform some network telemetry analysis. So we're looking at the extended TCP and UDP tables on the system to get a list of all the active network connections which are being made. These also come with process IDs, so we're able to map these network connections to our process telemetry to sort of paint a picture of what the user mode processes on the system are doing in terms of like C2 behavior and network callouts. And so this directly informs sorts of the attacks like EDR silencer, for example, where we're blocking the network telemetry or we're blocking the network connection from an EDR agent to a C2. So that's the relevance of our network telemetry to the attack surface. Moving on, we also perform some registry enumeration as part of the tool. So we enumerate a number of sort of hard-coded registry locations looking for configuration and other information like that. The registry is a gold mine for EDR in terms of the EDR attack surface. For those that aren't familiar with the mini filter altitude collision attacks from last year, as part of the kernel mini filter registration process, the mini filter needs to register an altitude value within the kernel where it runs at runtime. And if two mini filters are registering the same altitude value, then only the mini filter that starts first gets to run. And so we can directly disable EDR agents leveraging these mini filter collision attacks, which is done via the registry. So we found that any enumeration that we do in the registry generally proves fruitful in some respect or another. Moving on to our ASMI provider analysis. So ASMI is the anti-malware scan interface. It's a facility in Windows which injects a DLL into user mode processes and provides infrastructure for processes to query pieces of data against these providers, and they generate a verdict as to the status of the data. So as part of the registration process for ASMI, you need to register in the registry. So we're able to enumerate the registry and find all the loaded ASMI providers on the system. So ASMI is interesting because it hooks into things like PowerShell. So if we see that an EDR agent is registering an ASMI provider, we know that maybe we want to avoid script-based attacks, for example, which paints a picture of the attack surface from that perspective. The next piece of analysis that we're talking about is service enumeration. So we're leveraging the Service Control Manager API here to get a list of all the services which are running on the system, along with their start commands and their users, the users which they're running as. And what we can leverage these services. Most EDR agents or some EDR agents will run their agent as a service. So we can do things like stop the service to disable the EDR agent, very basic stuff like that. It doesn't work now for the most part, but the telemetry is still interesting in that respect. Similarly, our user context and privilege analysis, we're just enumerating all the users on the system, looking for things like system users for an EDR, for example. So some of the other telemetry that the tool generates is used for just general VM baselining. So if you're performing this sorts of testing across a number of VMs with different EDRs installed, these features become more useful. So things just like looking for memory protection settings, different kernel integrity checks, and stuff like that. Yeah. So in summary, I just wanted to give you guys Surveyor's value proposition. So we're collecting a pretty comprehensive reconnaissance profile as a big JSON dump. The information is useful from a red team perspective and a blue team perspective. So we can identify security gaps and exploitation opportunities. We can understand protection capabilities and operational limitations. And the critical insights that I wanted to leave you folks with are that EDR kernel callbacks are a primary mechanism for EDR monitoring. So understanding which kernel callbacks are being run on the system is crucial to understanding the attack surface from that perspective. ETW is a gold mine for behavioral analysis. So understanding which ETW sessions are being consumed directly informs the attack surface from that perspective. PPL, or process protected light, is directly informs the attack surface of the user mode processes on the system. And finally, the registry is a gold mine, so anything you find in the registry can likely be used in some attack or another. Thank you. So the project is live on GitHub at this link you folks can find in the slide. Check us out. It's a living project as part of the work that Jacob and I are doing day to day. So hopefully we'll be able to add some cool new features, stuff like doing dynamic PPL data lookup, so it's not hard-coded against a particular Windows build, and stuff like that. So yeah, there's a release on the GitHub page if you folks want to download it. The driver's unsigned, so act accordingly. This is meant for lab work. This isn't meant for any like real reconnaissance. So yeah. I'll throw it back to Jacob.
Okay. Yeah, I want to pick up the pace a little bit because I want to show you some actual bypasses. So obligatory MITRE attack shout out. Most of the EDR bypasses are kind of documented under the defense evasion tactic. However, they are kind of, there are some that we've worked with that are not covered there, and we actually found it useful to have a little bit more of a granular categorization. So we made our own kind of version of a matrix. Right now we have about 6 categories in there. Like the details don't really matter. It's still a work in progress. But we are kind of tracking, over the past 6 months, we've tracked all the different bypasses that have been published, and we're kind of trying to categorize them and systematically put them in different kind of places where they belong, and it makes it easier to work with them. So let's take a look at a few. First one we're going to take a look at is in the pre-execution category, and it's called a boot execute bypass. And the idea is, I'm an attacker, and I want to disable the kernel driver for the EDR. The reason we want to focus on the kernel driver is because that is usually where the EDR agent's tamper protection is implemented, and it's also where the kernel callbacks are, which is the main way that EDRs have visibility into the system. So if we disable the kernel driver, we really cripple the EDR product itself. So that's usually the high-value target. So the idea here is we want to disable the kernel driver by deleting the actual file from disk. If you just go into the command line or like File Explorer and try to delete the driver, you won't be able to. And it's important to understand the reason why. And it's usually not the file permissions, because you're the local admin, you can give yourself permissions to delete the file. But the kernel driver itself, the self-protection mechanism, will block you. It's like a mini filter driver. It will be able to intercept any file I/O calls to that file, and will be able to block it. So the idea is we want to delete that file during the boot process of Windows before the EDR's kernel driver is loaded. And so one way to do it is in the registry, there's a key called boot execute. There's already usually some values in there. There's an auto check utility that runs at boot time. It's kind of like a check disk utility, but you can actually add your own program in there and it will get executed during boot time. The caveat with that one is that the full Windows environment isn't loaded yet, so you have to have a binary that's called, it's so-called native API binary. These days with AI, it's not difficult to produce those. You can just tell Visual Studio Copilot to make one for you. And so if you drop that binary into C Windows System 32, add it to that registry key, and then reboot the system, during the next boot, it will delete the file, right? And so that works against most of the major EDR solutions in the market. Next one we're going to look at is from the policy abuse category. And the idea here is, I spoke before about WDAC, that's Windows Defender Application Control. I believe that's the successor to AppLocker. And one neat feature of this is that it has the ability to implement both application policies and kernel policies. And one of the things you can do with the kernel policies is to block certain drivers from being loaded. And so you can probably see where I'm going with this, right? So you can make, the attacker can make a policy, a kernel policy, and set it to block the EDR's kernel driver. Once you do that, you can use that wizard to compile a policy file, plant it into the appropriate location in the Windows folders, and then during the next boot, the EDR's kernel driver will be blocked and won't load. And again, this is something that works against most major EDR products. And another one that's interesting is service manipulation with a slight twist. So, this looks really basic. So in the registry, you have kernel drivers are loaded via services, the service mechanism. So for every kernel driver, there's usually a service. And in the service key, there's usually a start value. And if you set that start value to 4, that means it's disabled. And if you reboot the system, then that service or that kernel driver won't load. Now, normally, if you try to modify that registry key, again, the kernel driver won't let you. It'll block that operation. But that doesn't mean you're stuck. So there's a trick that you can use. And the trick is that instead of using the normal registry operations like modify a key or modify a value, there's another way to accomplish this. And that's using the save and restore registry operations. So the idea is you save the key that contains all the values that you want to change, and basically that will save it to a Hive file on disk. Then you can load that Hive file under a temporary key in the registry, make your modifications. This time the EDR's kernel driver won't block you because it's on a path that it doesn't care about. And they can save it back to the Hive file, and then restore content from that Hive file over the original service key. And it turns out that some EDR kernel drivers don't monitor for that, don't see that, don't block it. You can use that trick to make any registry modification you want without being seen for those EDRs that have that blind spot. I won't mention the actual products that are vulnerable to this, but if you're wondering which ones, you're probably right. One interesting thing that we actually found when we were looking at this is that one particular major EDR product was very resistant to any changes that we made to the registry for its keys. Anything we tried just didn't work, and we just couldn't explain it. We even kind of took the registry key from the system where the EDR was onto a different system that had no EDR, had nothing. And we still weren't able to modify those registry keys, and we were just racking our brains. What the heck was going on? And so it turns out after a lot of investigation that we ran into an undocumented feature in Windows that this particular EDR vendor was using. And it's called process trust level. And it's basically like an invisible setting in the permissions security descriptor. So you can see on the screenshot, what the normal security descriptor looks like in the properties. There's an invisible part that is not shown, but that EDR vendor was using, and essentially it made it impossible to modify those registry keys unless you were running from a PPL process. And so we actually made a tool to be able to kind of display those registry settings. So if you want to check your favorite EDR product, if it's using that, then you can use that tool. The link is over there. Okay, we're kind of running out of time. I'm going to skip over this one. We kind of built a sandbox lab to kind of automate and make the testing more efficient. But the interesting part is here. So I mentioned that we were kind of doing this systematic testing. So one of the most popular bypasses that attackers use, and we actually see this in the wild quite often, is they will try to disable the EDR by booting the system into safe mode. And the idea behind that is in safe mode, third-party kernel drivers don't load, which means that the EDR kernel driver won't load. All of the tamper protections will be disabled. The attacker, before they boot into safe mode, they will install some remote access product that still works in safe mode, so they'll be able to reconnect and access the system. Now the EDR will be disabled. They will, do some kind of permanent change to disable it permanently, boot back into normal mode, and now the EDR is disabled. So that's kind of the basic way the attack works. There's multiple ways to do this. The standard one is the BCD edit utility. Another one is the msconfig application. Recent versions of Windows also have a PowerShell commandlet to do this. And it just, it works. The problem is that some EDRs now block this action. They have, they have a setting that you can turn on to block this. And there's also a Microsoft attack surface reduction rule that tries to block safe mode booting because of this. So those are the mitigations. Unfortunately, there's a little bit of security theater. the one that we tested from a major EDR vendor. So basically, it blocks you the first time when you try it, but all you have to do is try to click on it again, and then it'll let you do it. So it looks like they didn't test it very well. Now the Microsoft one is not much better. It will actually block the BCD edit version of the attack, but if you use something like msconfig, it won't block you again, right? So it's a little bit of security theater. Now, if you actually run into something that will block it effectively, there are other ways of achieving the same thing. There's some nice research by Jeff Chappell that actually figured out what BCD edit and all those tools actually do behind the scenes. And it turns out that all that boot information is in the registry under the BCD key, which stands for boot configuration database. And there's a certain structure to this. And the upshot of it is that you can basically directly edit the registry and achieve the same thing that you do with those utilities. And that bypasses pretty much every EDR that we've tried. But if it doesn't, you can go even deeper. And you can actually edit the Hive directly itself on the file system. It's hidden in the system partition. Usually it's invisible. But if you use the diskpart tool to assign a drive letter to that partition, you can actually access that file, and you can copy over your own version if you want. And that's an even stealthier way of doing this. So that's just one example of the kind of testing you can do and how far you can get. A, B, C, D are some of the major EDR products that we tested. And so you can see the results that certain variants work against every single one that we've tested. And this is pretty much par for the course for the sort of EDR bypasses that you can find if you look. So what do we do with this information? We have contacted some EDR vendors with some of the findings that came out of it. Some of them have been fixed in the past. There's others that we haven't reached out with yet, but we will. Internally, we also develop detection rules. We have our own EDR agent that we can build detections for some of these attacks in, and so we're working on that. And it also helps us to develop redundant monitoring mechanisms, right? So if the EDR fails, you should have some other way of monitoring the system, whether it be network or logs or potentially, a second agent in parallel, which is sometimes what we do. Essentially, you need to plan for your EDR to fail. I'm going to skip past this. So key takeaways. EDRs are now routinely being attacked. So, we see that very often now in real intrusions. It's a large, complex attack surface, so it's very difficult to lock everything down. And you're pretty much guaranteed to find something for every product. Vendors should keep up with the arms race and at least make it harder, because essentially what you're trying to do is buy time. The longer it takes for the attacker to find a bypass, the more time you have to trigger some sort of alert, trigger some sort of response, and hopefully kick them out of the system before they're able to get far enough. And of course, you have to be aware that EDR at this point buys you time, but it will never guarantee full prevention, right? So, thank you very much.